Welcome to the session. So this is N.Selvam, working as Assistant Professor in Electrical and Electronics Engineering, M. Kumarasamy College of Engineering, Karur. So today we are going to discuss about the topic of protection against lightning. What are the devices we are going to use in order to protect our circuits from lightning and switching? Let us discuss. So normally we know that so switching which is nothing but suddenly switching on all the devices or suddenly switching off all the devices. So this will create transient surge on your power system, right? And coming to the external causes, so which is nothing but lightning, right? So lightning which is occurred due to the external causes, right? So first of all we need to know about what is transient, right? So transient or surge on the power system may originate from switching and from other causes, but the most important and dangerous surges are those which is caused by lightning, right? So among the switching and lightning, so the lightning which creates dangerous surges, right? So we need to provide protection against this lightning, otherwise it may cause damage to our apparatus which is present in our power system, right? So the lightning surges may cause serious damage to the expensive equipments in the power system. For example, in our power system we have generator, transformer, so motor, and then circuit breakers, bus bar, and then feeders, right? So in our power system we have this number of apparatuses. So if you are protecting our power system against these causes, then we can easily protect our apparatus. But if you are failed to give protection against these two lightning and then switching, then it may cause damage to our apparatus which is present in our power system, either by the direct lightning strokes on the equipment or by the strokes which is on the transmission line that may reach the equipment as a traveling waves, right? So if it is directly causes the equipment, means that is called as direct lightning strokes. But so instead of direct lightning strokes, if the strokes or lightnings are falls on the transmission line, so that and then which travels to the that will reach the equipment through the transmission line, means it will called as traveling waves. So we need to provide protection against these two problems, right? And then it is necessary to provide protection against these both kind of surges, that is over voltage which is created due to lightning, and then the over voltage which is created due to switching. And then the most commonly, so we need to provide protection to our aim in this topic is we need to provide protection against the electrical apparatus which is available in power system against this lightning as well as switching. So the most commonly devices which is used for protection against lightning surges are, so first one is earthing screen, second one is overhead ground wire, and third one is lightning arrestor, are also called as surge diverter, right? So let us discuss each devices one by one in detail. So first of all we just overview about these devices. So earthing screen which is mainly used to provide protection to the power station and substations against direct lightning strokes. So whereas you can coming to the second device, that is overhead ground wire, so which provide protection against the direct lightning strokes to the transmission lines, right? But however the lightning arrestor are such diverters which provide protection to the station apparatus against both direct lightning strokes and the strokes which is come into the apparatus as a traveling waves. So from this we can easily conclude that, so in the earthing screen which is mainly used to provide protection to the power station as well as substation against the direct lightning strokes. But the second device which is mainly used to provide protection to the transmission line against direct lightning strokes. So the first method and then the second overhead ground wires are used to provide protection against direct lightning strokes. But coming to the lightning arrestor and then surge diverter, so these two devices are used to provide protection against station apparatus against both lightning strokes and then direct lightning strokes and then indirect lightning strokes, right? So first one is earthing screen. We know that in the power stations, substations generally consist of expensive equipments, right? So these normally in our power station and substation we have number of transmission lines, transformers, and then the lightning arrestor protection devices, so which consist of so many expensive equipments. So these stations can be protected against direct lightning strokes by providing earthing screen. So the earthing screen, which consists of a network of copper conductor, which is generally called shield or screen, which is mounted all over the electrical equipment in the substations or power station. So the shield is properly connected to the earth on at least 2 points through the low impedance. So on the occurrence of any direct lightning strokes on the power station or substation, so this earthing screen which is available, we know that we are installing that earthing screen in the power station as well as substation. So whenever the fault is occur or direct lightning strokes are fall onto the station, so automatically in the earthing screen which provide low resistance path by which the lightning surges are conducted to the ground, right? So that is why we are installing the earthing screen in the power station. So whenever if you are installing that, so on the occurrence of any direct lightning strokes on the power station, so that lightning strokes or extra surges are diverted to the ground through this low resistance path. Then coming to the, so this is an operation of earthing screen. Then coming to the limitations of this method is that, so it does not provide protection against the traveling waves because which may reach the equipment in the station, right? So that is the one limitations of this earthing screen. It provides protection only against the direct lightning strokes, right? Then coming to the second method, that is overhead earth wire. So for the simplicity, here we have this is a schematic representation of our overhead transmission line protection. So for the simplicity here, only a one ground wire and then one line conductor are shown. So instead of the three phases, here only the one phases is shown. So the ground wires are placed above to the line conductor at such position that practically all the lightning strokes are intercepted by them, right? So the ground wires are grounded at each tower or pole through the low resistance as possible. So due to their proper location, the ground wire will take up all the lightning strokes instead of allowing them to line conductors. So whenever the lightning strokes occurs on the transmission lines, here you can look at this schematic diagram. Here we have so this is our tower. See, here we have one line conductor, and then in above to our line conductor we have shown the ground wire, right? So this is a structure of ground protection, ground wire protection. And then whenever the lightning strokes which is occur on the transmission line, so what will happen? It will be taken up by the ground wires. So whenever if the, so you can look at here we have cloud. So whenever the lightning is occur on this line means if it is fall onto the line conductor means, so before to the line conduct, before reaching the line conductor, and the lightning strokes will face the ground wire. So whenever instead of this line conductor, if the lightning strokes fall on the ground wire means, so it will divert this extra surges through the towers. So here at the each at some space we have spacing, we have connected one tower. So due to that tower, so that tower is grounded through the some footing resistance. So if the lightning strokes is fall onto the line conductor, so in before that we are installing the ground wire, so that by using this ground wire, that lightning strokes are diverted through this tower and then this footing resistance. So in this way here we are providing protection to our electrical apparatus which is present in our transmission lines and power systems with the help of overhead ground wire, right? And then so it may be mentioned here that, so the degree of protection which is provided by the ground wire, which is mainly depends upon this footing resistance of the tower. So in every tower we are installing one, we are grounding that one lead of our tower to the ground through the footing resistance. So here the footing resistance at tower 1 is R1 and tower 2 is R2, right? So whenever the lightning strokes are fall onto the ground wire, then it will divert that extra strokes through the low footing resistance with the help of this tower which is installed at the each tower, right? Then the next one is lightning arrestor. So the third device is lightning arrestor. We know that, so this lightning arrestor is also called as surge diverter. So this surge diverter, which is mainly used to provide protection against both direct lightning strokes and then indirect lightning strokes, right? So in previously discussed two methods, that is the one is earthing screen and another one is overhead ground wire, which are very suitable for protecting an electrical power system from direct lightning strokes, right? But you can commit. So but the limitations of above two methods is it does not provide protection against the over voltage which is created due to the indirect lightning strokes, right? So that is why here we are go with this lightning arrestor, right? So in previously discussed method we have earthing screen and overhead ground wire, which are very suitable for protecting an electrical power system from direct lightning strokes. But the system from the direct lightning strokes, these methods cannot be provide any protection against high voltage traveling waves which may propagate through the line to the equipment of the substations, right? So the lightning arrestor, which is nothing but it is a device protecting devices which provide very low impedance path to the ground for very high voltage traveling waves, right? So the main role of this lightning arrestor or surge diverter, which provide a very low impedance path to the ground for this extra surge voltages, that means high voltage traveling waves. So the concept of this lightning arrestor is very simple. This device behave like a non-linear electrical resistance, and the resistance decreases as voltage increases, and vice versa. If the resistance increases, automatically the voltage decreases, right? So after a certain level of voltage. So the function of a lightning arrestor or surge diverter can be listed below, right? So the first one is, so under the normal operating condition, so this lightning arrestors withstand easily by the system voltage as an electrical insulator, and which provide no conducting path to the system current. And on the occurrence of any voltage source in the system, so this device provide a very low impedance path for excess charge of the surge to the ground. So very simple. So during the normal operating condition, here you can look at the diagram of lightning arrestor. Here we have power circuit. So one end of, so this is our spark gap, so which is grounded. So this combination, this power gap and then this non-linear resistor, and the combination is called as lightning arrestor devices. So this lightning arrestor non-linear resistor is connected to the ground through the very low impedance path, right? So whenever so here we have some in between these two, we have maintained some spacing, right? So during the normal operating condition, what will happen? We don't have any sufficient surge to create this power gap, right? So at the time, what will happen? So these lighting devices withstand easily by the system voltage as an electrical insulator. So during the normal operating condition, this lightning arrestor is operate as an insulator, so which provide no conducting path to the system ground. But on the occurrence of any voltage surge in the system, so the working voltage will be increased than our normal system voltage, right? So these at the time, these lightning arrestor which provide a very low impedance path for the excess charge of the ground to the ground, right? So on the occurrence of fault, what will happen here? Due to the extra high voltage, so here the spark is created. So if it is spark is created, then the spark gap will be conductor. So if it is conductor means, so the surges which is present on the power circuit, which is diverted to the ground through this non-linear resistor. So this is a working principle of lightning arrestor, right? So these are all the methods which is mainly used to provide protection against over voltage which is created due to lightning as well as switching, right? So that's all about this topic. And then the next topic is protection of electrical apparatus against traveling waves, right? So here in order to provide protection to the electrical apparatus which is presented in electrical power system, we need to use against the traveling waves, we need to use some methods, some lightning arrestor, right? So because in previous topic we discussed three methods. In among the three methods, the first two methods is used to provide protection against direct lightning strokes, but the last method, that is the lightning arrestor, only is used to provide a protection against the indirect lightning stroke, that is nothing but against the traveling waves. So that is why here we are going to use the types of lightning arrestor to provide protection to the electrical apparatus against traveling waves, right? So here we have four types. So one is rod gap arrestor, second one is horn gap arrestor, third one is multi-gap arrestor, and fourth one is expulsion type lightning arrestor. Right, so let us discuss each type of lightning arrestor in detail. And first one is, it's a rod gap arrestor. Right, so it is a very simple type of diverter, and which consists of two 1.5 centimeter rods, so which are bent at right angles with the gap in between, which is shown in the diagram. Right, so here you can look at here we have transformer tank, and this is the transmission line. Right, so in between here we are using the transmission pushing. So at the transmission line at the top end we have connected one rod, and then below we have connected one rod. Right, so which is one rod is connected to the earth and one rod is connected to the line. So in these two rods, which consist of the length of 1.5 centimeter, and these two rods which are bent at right angle with the gap which is in between, like this. Right, so here in between these two we have maintained some gap, and then from the this rod and to the transformer pushing we need to maintain some distance. That distance is described by letter P. Right, so one rod is connected to the line, as I said before. The one rod is connected to the transmission line circuit, and then the another rod which is connected to the earth. So the distance between gap and then the insulator must not be less than the 1/3 of the gap length, so that the arc may not reach the insulator and damage it. So what they told us, so here we need to maintain some distance between this rod and then this transformer pushing. Right, so that is the 1/3 length. Right, so if you are not maintaining that distance, means what will happen, it will create spark to this, it will create spark to the transformer pushing, then it will damage it. So in order to avoid this, we need to maintain some distance between the rod and then the transformer pushing. Right, and then so generally the gap length is so adjusted that the breakdown should occur at 80% of spark over voltage in order to avoid cascading of very steep wave fronts across the insulators. Right, so in the string of insulators for an overhead line and the pushing of transformer has frequently a rod gap across it. Right, and then you can look at this diagram here, which shows the rod gap which is across the pushing of the transformer. Right, so under the normal operating condition the gap remains non-conducting, because under the normal operating condition the normal working voltage is flow through the transmission line. At that time it does not conduct this gap. Right, so on the occurrence of, so the gap between these two rods is non-conducting, because no spark over is created here. Right, but on the occurrence of any high voltage surge on the transmission line, what will happen, so whenever the extra surges is created here, at the time that extra surges are started to flow through this rod to the ground through this way. Right, so if the extra surges is created and diverted through this rod means what will happen, this extra surges will create the spark over between these two rods. So it will then at the time so it will conduct, the rod gap will conduct, the spark over is created, so that will conduct this two rods. Right, so that spark over is created, and then the surge current is conducted to the earth. Right, so in this way the excess charge on the line due to the surge is harmlessly conducted to the earth. So this is an first method to provide protection to the electrical apparatus against the traveling waves. Right, so simply during the normal operating condition what will happen, the gap remains inoperative, so it does not conduct. Right, but on the occurrence of any fault the extra surges started to flow through this rod, so at the time this rod is started to conduct, so the spark over is created. So due to that spark over, here the gap is conducted. So if it is conducted means the extra surges which is fall onto the transmission line started to divert to the earth. Right, so this is a working principle of rod gap arrestor. And then the second one is horn gap arrestor. Right, so this is a diagram of horn gap arrestor. So you can look at this diagram, which consists of two horn shaped metal rods. So here we have one horn shaped metal rods, and here also we have one horn shaped metal rods. So one is described as A and another one is B. So these two metal rods are separated by a small air gap. So you can look at here we have one metal rods and here we have one metal rods. So in these two metal rods are separated by some length. right? So that is nothing but air gap. So the horns are so constructed that the distance between them gradually increases towards the top as shown, right, as shown in this diagram. You can look at this. Here we have some spacing in between these two metal rods. So at position 1, the distance between these two metal rods is less, but you can come into the position 2, the distance between the metal rods A and B is somewhat increases than your position 1. But you can move to the third position, the distance between that means the air gap between your metal rod, horn shaped metal rods A and B, it will be increased than your 1 and 2, position 1 and 2. So if you are look at the upward direction, so the spacing will be increased, right? So and then so the horns are mounted on the porcelain insulator. So these two horns are insulated on the porcelain insulators, right? One end of horn which is connected to the line through a resistance R and then the choke L, while the another end is effectively grounded, right? Now you can look at this diagram. Here the one end of your horn gap which is connected to the line through the resistance. So here we have a line, right? So which is the end is connected to the apparatus to be protected, right? So this one end, that is in the metal rod A, which is connected to the transmission line through the resistance R and then the choke coil L, right? While you can look at this another end, so which is effectively grounded through the some resistance R through some low resistance path, right? And then here the resistance R which helps to limit the follow current to the small value. So here the resistance is used to reduce the following current, right? And then here the purpose of this choke coil is so designed that it offers very small reactance at normal power frequency but very high reactance at transient frequency, right? So the purpose of this resistance and the choke coil is, so the resistance is mainly used to oppose the follow-up current, and then the choke coil is mainly used to provide very small resistance at normal power frequency and very high reactance at transient frequency, right? So thus the choke does not allow any transients to enter into the apparatus to be protected. So the main purpose of choke coil is it does not allow the transient surges to enter into the transmission, because in the another end of your choke coil is connected to the transmission lines, right? So in the transmission lines only we have some apparatus, right? So this choke coil does not allow the transient surges to enter into the apparatus, right? And then the gap between these two horns is so adjusted that the normal supply voltage is not enough to cause an arc across the gap. So and under the normal operating condition, the gap is non-conducting, that is the normal supply voltage is insufficient to initiate the arc between the gap. So we know that already I told before, during the normal operating condition we don't have sufficient voltage to create this arc, right? So if an arc is not created, means what will happen? So in the normal operation is continuous, right? But on the occurrence of any fault, at that time what will happen, or any surges is created, at the time we have enough voltage to create the arc between these two metal rods. So at that time what will happen, here we have maintained some spacing between the two metal rods. So here we have some if arc is created, means surrounding the arc which will dissipate the heat. So due to that heat, we have some air circulation. So due to that air circulation, in the arc is started to move upwards. So at position 1 the length of the arc is increased, and then again it started to move to the position 2. At that position the length of the arc is somewhat increases, and then again it is moved to the position 3. So at position 3 and the length of the arc is increased. If the lengthening of arc is increased, means what will happen, the dielectric strength of your arc is reduced. At the time the arc is automatically extinguished, right? So during the normal operating condition, so the arc is not created due to the insufficient supply voltage, but on the occurrence of fault we have sufficient voltage to maintain the arc. So at the time the arc is created in between these two metal rods. Then if the due to the air, heat and air circulations, air insulation, if the arc is started to move upwards, at position 1 the length is increased, and then 2 it is again increased, and then 3 increased. If the arc length is increased, means automatically and the dielectric length of your arc is decreased. If is the dielectric length decreased, means automatically the arc which is available at position 3 is automatically extinguished. So the fault is disconnected, right? And then the third one is multi-gap arrestor, right? So this is a diagram of multi-gap arrestor. So it consists of series of metallic cylinders. So here we have A, B, C. So these three are the metallic cylinders which is insulated from one another, right? And then which is separated by the very small intervals of air gap. So this is our series gap and this is your shunt gap, right? So in the first cylinder, that is A, right, so which is connected in series with the transmission line, and the another one is connected to the ground through the series resistance. So here the second cylinder is connected to the ground through this series resistance. So the purpose of the series resistance is to limit the power arc, right? So by this inclusion of this series resistance, the degree of protection against the traveling waves is reduced, right? So in order to overcome this difficulty, some of the gaps B to C which are shunted through the this resistance, right? So that is why we are going for multi-gap arrestor, right? And then coming to the fourth one, that is expulsion gap type arrestor, so which is similar to the rod gap arrestor, right? So here this type of arrestor, which is also called as protector tube, so which is commonly used on the system operating at voltages up to 33 kV, right? So this method is mainly used on the systems operating at voltages up to 33 kV, right? And then so this is an essential part of your expulsion gap lighting arrestor. It essentially consists of a rod gap A. So here you can look at here we have gap A and the rod gap A2. So A and then A dash, so which is connected in series with the second gap, right? So here we have one gap and here we have another one gap. So the second gap is called as internal gap, right? So which is the first gap is connected in series with the second gap, right? You can look at the second gap which is enclosed with the fiber tube. So this is your second gap. So this gap is insulated with your fiber tube. So the gap in the fiber tube is formed by two electrodes, right? So the upper electrodes is connected to the rod gap and the lower electrode is connected to the ground. So here we have as I said before, here we have two electrodes. One is connected to the transmission lines and another one is connected to the ground, right? So one expulsion arrestor is placed under each line conductor. So under the every line conductor, so we have to install one expulsion arrestor, right? So in the installation of expulsion arrestor on the overhead line, which is shown here, so this is an installation diagram. See, on the occurrence of any over voltage on the transmission line, what will happen? So in the series gap A and A dash is spanned and then the arc is stuck between the electrode in the tube, right? So during the normal operating condition, what will happen? So we don't have any sufficient voltage to create this arc between these two rod gaps. So the gap remains open, right? It does not conduct. So first gap as well second gap does not conduct during the normal operating condition. But on the occurrence of an over voltage on the transmission line, so what will happen? So in the series gap A dash is spark over due to the extra surges, so it will conduct. Then that extra surges started to flow through this rod and then which is again diverted to the second gap through the electrodes, right? And then this A2 is spanned and then here also the arc is created in between these two electrodes in the tube, right? So if it is arc again, the arc is stuck between these two second gap, means what will happen? It will create arc. So due to that arc, the heat will be surrounded. So that heat of an arc which vaporizes some of the fiber of tube wall. So here we know that the second gap is surrounded by the fiber tube. So in between these two gap, if the arc is created, means it will dissipate some heat. So that heat of the arc which vaporizes some of the materials of your wall, so resulting in the production of neutral gas. So due to that neutral gas, it will be conducted, and then the extra surges is diverted to the earth. Right. So due to after the diversion of these extra surges and the production of neutral gas, and the arc is extinguished. Then after the clearing, diverting all the surges, the gap 1 and 2 is still in open condition. Right. So this is a working principle of expulsion type arrestor. Right. So and then next one is a surge absorber, and the surge absorber, which is nothing but it is an protective devices which is used to absorb the complete surge, which is due to the lightning surge or any transient surge in the systems. Unlike the lightning arrestor, in which the nonlinear resistor is provided, which provides a low resistance path to the dangerously high voltages on the system to the ground. Right. So here in the surge absorber, this is the diagram of surge absorber, which consists of one air core inductor and then dissipator. Right. So here this air core inductor is surrounded by some dissipator in the cylindrical shape. So in the one end of air core inductor, which is connected to the ground, and another one is connected to the substation. Right. Here, so this surge absorber, coming to the working principle, so this surge absorber is working as an transformer, air core transformer, because here we have air core inductor and then dissipator. So transformer means we have two windings. So the air core inductor is act as a primary winding, and the dissipator is act as a secondary winding. So the role of this surge absorber is act as an air core transformer. So whenever the lightnings extra surges are created, so it will flatten that arc, and which is diverted to the ground with the help of this connection. Right. And then so that's all about this absorber. So the next topic is the methods of earthing the neutral point of the system. So before going to earthing the neutral point of the system, first of all we need to know about the what are the method, what is earthing, and what are the types of earthing in our power system. Right. So first of all we need to know about what is earthing or right. So the process of connecting the metallic frame, that is, if it metallic frame means that is non-current carrying part of your electrical equipment, or some electrical part of the system. So electrical part of the system means, for example, the conducting part, that is in the neutral point in the star connected system. So that neutral point is conducting, but the metallic frame, which is nothing but it is an outer cover of your machine, so it does not conduct. Whenever this fault is occurred, at the time it may be there may be a chance to conduct that metallic frame, but actually it is the metallic frame is a non-current carrying part. Right. So in the process of connecting the metallic frame of electrical equipment or otherwise some electrical part of the system to the earth, which is called as grounding, or also called as earthing. Right. So metallic frame, which is nothing but non-carrying part of electrical equipment. If it is an electrical part, means neutral point of star connected system, or one conductor of secondary of the transformer, etc. So we need to connect that point to the earth. So the earth is, which is nothing but soil. So this process is called as grounding or earthing. Right. So based on the part, that is the frame or the point which is connected to the earth, so it can be classified into two types. One is equipment grounding, and second one is system grounding. Right. So first of all we discuss about what is equipment grounding and system grounding, then we will go with neutral grounding. Right. So equipment grounding, which is nothing but the process of connecting non-current carrying metal parts of electrical equipment to the earth in such a way that in case of insulation failure, the enclosure effectively remains at earth potential, is called as equipment grounding. So equipment grounding means we have to connect the one part of the equipment to the earth. So the equipment, which is nothing but non-current carrying part. Right. So if you are connecting that non-current carrying part to the earth means that is called as equipment earthing. If it is system earthing means, so instead of non-current carrying part, if you are connecting the some electrical part of your power system to the ground means that is called as system grounding. So this is a difference between the system grounding and then equipment grounding, right? If you are connecting the non-current carrying part to the earth means that is called as equipment earthing. If you are connecting the some electrical part of the power system to the ground means that is called as system grounding, right? And then the next is neutral grounding, right? So neutral grounding, which is nothing but the process of connecting the neutral point of three-phase system to the earth, right? So either by directly or through some circuit elements is called as neutral grounding, right? So the neutral grounding which provide protection to the personals and then as well as equipments. So it is because during the earth fault the current path is completely through the earth neutral, and the protective devices example fuse etc. which operate to isolate the faulty conductor from the rest of the system. So this point is illustrated in this diagram. Alright, so here in this diagram you can look at here. So here we have neutral point, means we have to connect the current carrying some electrical conducting point of your electrical system, right? So here we are showing the three-phase star connector system with neutral earth to neutral point is earth, right? Suppose if there is any single line to ground fault is occur in this line, for example from R to the ground means, so what will happen? So this will cause the current to flow through the ground path as shown in this diagram, right? So note that the current from phase R to the earth, then which is again diverted to the neutral point N, and then we again which is coming to the R, right? So if you are allowing this, it will cause damage to the equipment which is presented in your power system, right? So coming to the advantages of neutral grounding. So here the voltages of the healthy phases do not exceed the line to ground voltages, and the second one is the high voltage due to the arcing which grounds are eliminated, and then that means the arcing grounds which is eliminated. So these arcing grounds are which is established due to the ungrounded three-phase systems. If the neutral point of your three-phase system is not grounded to the earth, so which may cause the arcing ground. So in order to eliminate that, we need to connect the neutral point to the earth, right? And then the protective relays can be used to provide a protection against earth faults. So in case of earth fault on any of the line, the protective relay will operate to isolate the fault line, right? And then it provides a improved service reliability, it provides greater safety to the personnel and then equipment. So these are all the advantages of neutral earthing. Then we will move to the what are the methods used in methods of neutral earthing, right? So the most commonly used grounding of neutral point of three-phase systems methods are the first one is a solid grounding, second one is a resistance grounding, third one is reactance grounding, and fourth one is Peterson coil grounding. So these are all the most commonly used methods in power system, right? So in the choice of method of grounding, which is mainly depends upon the many factors, which includes the size of the systems, system voltage, and then the scheme of protections to be used. So based on these three methods, the choice of method of grounding may be vary, right? So let us discuss the each grounding method in detail. So first one is the solid grounding. So solid grounding, which is nothing but when the neutral point of your three-phase system, for example three-phase generator or three-phase transformer, if you are connecting the neutral point of that three-phase system to the earth directly through a very small wire having the negligible resistance or reactance, then it is called as solid grounding. The another name of solid grounding is effective grounding, right? And then so this is a diagram of your solid grounding, right? So in this diagram, the solid grounding is represented. Solid grounding means if you are connecting the neutral point directly to the earth, means that is called as solid grounding. So since the neutral point is directly connected to the earth through a small wire, so the neutral point is held at earth potential under all conditions. So therefore any fault is occurred, the voltage of any conductor to the earth will not be exceed the normal phase voltage of the system. Right. So here we have three phase systems. So here the one end of all the three phase windings are connected together, so that is called as neutral point or star point. If the neutral point is directly connected to the earth without any resistance or reactance, so that is called as solid grounding. Right. Then coming to the second method, that is resistance grounding. So in order to limit the magnitude of earth fault currents, we need to go for resistance grounding. The limitations of solid grounding is, in that solid grounding method, we are not able to limit the magnitude of fault current, but that limitations is overcome in this method. Here it is mainly used to limit the magnitude of earth fault current, right? So, and it is a most common practice to connect the neutral point of three-phase system to the earth through a resistor, very small resistor. So if the neutral point of the three-phase system is connected to the earth or soil through some resistance, means that is called as resistance grounding. Right. So here, when the neutral point of three-phase system, that point may be a three-phase generator, one end of three-phase generator, or the neutral point of a three-phase transformer, which is connected to the earth through a resistor, that is called as resistance grounding. So this is a diagram of resistance grounding. Here the neutral point is connected to the earth through the very small resistance, right, having some value. So based on the magnitude of fault current, so this resistance value may be varied. Right. So the main function of this resistance is to limit the magnitude of fault current. If the magnitude of fault current is high, means we need to increase the value of resistance. Right. Then the value of resistance R should neither be very low nor very high. Right. So if the value of earthing resistance R, which is represented here, is very low, means the earth fault current will be large. Then the system becomes, which is similar to the solid grounding system, right? So if you are connecting the resistance having very small negligible resistance, means it is very similar to your solid grounding, right? So if because resistance having the very small value is not able to protect the in order to avoid this magnitude of fault current, right? And the another hand, so if the earthing resistance is very high, means what will happen? It opposes the magnitude of fault current. So then the system conditions becomes very similar to the ungrounded neutral system. So the value of R is to be chosen that the earth fault current is limited to the safe value, but still sufficient to permit the operation of earth fault protection system. So this is an operation of resistance grounding, right? And then the third one is reactance grounding. So the difference between the resistance grounding and then the reactance grounding is that very a single difference, that so in this reactance grounding, reactance is inserted between the neutral and then the ground, right? So here in solid grounding, we are connecting the neutral point of the electrical system directly to the ground, so that is called as solid earthing. And then the second method is resistance earthing. The neutral point of the three-phase system is connected to the earth through the resistance, right? So that is called as resistance earthing, right? So coming to the third, that is reactance grounding, the main difference is between the previous method and this method is, instead of resistance, if you are connecting the reactance, then that is called as reactance grounding, right? So the purpose of this reactance is to limit the earth fault current, and by changing the earth reactance, we can able to control the earth fault current, right? So based on this value, this earth fault current may be changed to obtain the condition which is similar to the solid grounding, right? So that's all about reactance grounding, right? So here only the, instead of resistance, we are using the reactance. Based on the magnitude of fault current only, the value of resistance as well as reactance is chosen, right? And then the final method is R suppression coil grounding or resonance grounding, right? So we know that the capacitive currents are very responsible for producing the arcing grounds. So due to the presence of capacitive currents only, the arcing current is produced, right? We know that what is arcing grounds. Arcing grounds means if in your three-phase system, if the neutral point is not connected to the earth properly, automatically it will create some current. So here, which may due to the absence of earthing, So in between the phases to the ground, one capacitance is formed, so it will produce the capacitive current. So due to that capacitive current, the arcing current is grounds is produced. That means arcing, right? So these capacitive currents flow because the capacitance exists between the east line and to the ground, right? And if the inductance L of appropriate value is connected in parallel with the capacitance of the system, the fault current IF, I suffix F, which is started to flow through the L, will be in phase opposition to the capacitive current of the system, right? So if L is so adjusted that IL is equal to IC, then the resulting current in fault will be 0. So this condition is called as resonance condition. So resonance condition, which is nothing but capacitive current is equal to the inductive current, means that is called as resonance condition, right? So when the value of L of arc suppression coil is such that the fault current IF exactly balance the capacitive current IC, it is called as resonance grounding, right? Then you can look at this circuit here, and arc suppression coil is shown. That is also called as Peterson coil, which is connected in between the neutral point and to the ground, right? Here in arc suppression coil we have some tappings, right? So here the purpose of reactor is to provide it with number of tappings to change the value of inductance. Then only we can able to achieve the resonant condition, right? So by adjusting this number of tappings on the coil, only we can capacitance value can be tuned. So the inductance value can be tuned with your capacitance of the system. So then only if you are tuned with your capacitance of the system, then only we can achieve the resonance grounding, right? So here so that is called as so that's all about the operation of arc suppression coil. So here the difference between this arc suppression coil and then the previous method is, in the arc suppression coil we are using the inductor which has number of tappings. By adjusting this number of tappings of the coil, we can easily tune up the value of inductive current with your capacitive current, right? Then if you are by changing the number of tappings in our arc suppression coil, we can easily make the resonant condition. If the resonant condition is achieved, then automatically it will create, so that is called as arc suppression coil grounding, right? So that's all about the neutral earthing and the various methods of neutral earthing. Okay, thank you.